Hi folks, this is Nat, and this is going to be your video lesson on solving division problems with non-terminating decimals. The very first thing that we're going to talk about is what exactly a non-terminating decimal is, and it's a pretty easy thing to explain when we compare it to what a terminating decimal is. By now, hopefully, you are used to the idea that some decimal answers, particularly with division, when you plug them into your calculator, do whatever you have been doing up to this point, give you a nice neat answer like 3 5/10, and that's it. That is an example of a terminating decimal. What that means is that that decimal place doesn't go on and on forever. It stops. Terminate means stop, so a terminating decimal is a decimal that stops. By contrast, a non-terminating decimal would be a decimal that goes on endlessly. The number pi is a great example of that. So the simple idea here is that terminating decimals are decimals that end, decimal values that end. Non-terminating decimals are decimal values that never end. They go on forever. And because they go on forever, we can't just keep dividing and dividing and dividing. We have to know how to handle those. Up to this point, you have mostly dealt with the idea of a division problem that doesn't go in evenly or doesn't end by using remainders. You might, for example, have said if I have 35 Skittles and I'm splitting them among 4 friends, well, the answer here is going to be 8, remainder 3. So you took that extra piece, that leftover, and just stuck it on the end and said, oh, and there's 3 left over. And that's a great solution for some problems. For example, this Skittle analogy, if I'm splitting up Skittles among my friends, probably I'm not going to take those 3 remaining Skittles and divide them into chunks that can be given to my 4 friends. So a remainder works really well in that case. There are lots of other cases, though, where remainders don't really make sense. If I'm traveling across the country on a plane or whatever, and I travel, 6,215 miles in 7 hours, and I want to know how many miles per hour is that, I can go through my division process and say, okay, well, 6 doesn't go in, carry the 6, 7 goes into 62 8 times, with 6 left over, 7 goes into 61, 8 times with 7 left over, 7 goes into 75. Must have made a mistake here. Yeah, this should be 5 left over. 7 goes into 55, 7 times. Well, now I've got leftovers again. I've got, what do I have this time? Got 6 left over. And in this scenario, it really doesn't make sense to say I'm traveling 887 remainder 6 miles per hour, because it actually does make sense to split that remainder up and say that every hour I traveled 887 miles and some fraction of a mile. And a remainder really isn't a fraction, so it doesn't express what I'm trying to describe here. So sometimes remainders won't work, is the big point. And this is one of those times. So increasingly what we have to get used to in math is the idea that we don't really see remainders all that much. That's why your calculator doesn't typically spit out remainders when you ask for the answer to a problem or when you plug in a problem to it. Remainders are not something that we use frequently in math after this point. So the question is, what do we do instead? Let's take our example here. We can solve this same problem all the way up to the point where we were and talk about what we're going to be doing now. 7 goes into 6 0 times with 6 left over. 7 goes into 62 8 times with 6 left over. 7 goes into 61 8 times with 5 left over. 7 goes into 55 7 times, and we have 6 left over just like we did before. Here's what we're going to start doing. Rather than calling this remainder, we're going to continue dividing. And we're going to add a decimal point if one's not already in there, because our decimal point always lives to the right of the whole number, and a 0. And we're just going to keep going. If necessary, we'll add a couple zeros. For example, when I take the 7, I'm going to tack that 6 onto the end and say 7 goes into 60 8 times with 4 left over. 7 goes into 40 5 times with 5 left over. And what I'm going to discover is that I potentially could keep going forever. 7 goes into 57 times, and then with 1 left over. So this is an example of a non-terminating decimal. It's going to go on forever and ever. So what I'm going to have to do with this ultimately is just decide to stop at some point. I can't spend the rest of my life dividing here, so I eventually have to decide to stop. And that really just depends on where I want to round to, or how specific I want to be with my answer. So at this point, I have a decision to make. I've got 887 in a non-terminating decimal. I could say I'm going to round to the 10th place, and I could call this 887 and 9/10. If I was rounding to the 10th place, I used my hundredths place to decide whether I rounded up or down. Alternatively, I could say I'm going to round to the hundredths place, and I could say 887 and 86 hundredths is my answer, using this thousandths place to help me decide about rounding. If I want to round to the thousandths place, I'm going to need to go one more digit in my answer. I'm going to have to take that, add an extra 0, carry what's left over, and do it again, so that I can then round to the thousandths place. So you're always going to solve the problem one place past where you want to round to. And this is really at this point how we're going to decide when to stop. Want to round to the 10th place, go to the hundredths. Want to round to the thousandths place, got to go to the 10,000ths. Want to round to the ones place, you go to the tenths. Always do your division when you have a non-terminating decimal one place past where you want to round to, so you know where to round. So here's an example of this. Let's say I want to solve the problem 321 divided by 4, and I want to round to the 10th place if necessary. I'm going to assume it's necessary. I'm going to go ahead and do division like normal up to the point where I run out of numbers. 4 goes into 3 0 times, so I'll carry the 3. 4 goes into 32 8 times with nothing left over. 4 goes into 1 0 times with 1 left over. So because I've got leftovers, I'm going to add a 0, a decimal, and a 0, and I can tack my 1 onto that. If you're doing traditional style division, it works the same way. You just add a 0, bring it down. 4 goes into 10 2 times with 2 left over. So I'm going to have to add another 0, and I'll tack the 2 onto that. 4 goes into 25 times. There's actually nothing left over. So this isn't a true non-terminating decimal. This is a terminating decimal. It actually ended right here. So if I was happy with that, I could just call it 80 and 25 hundredths. If, on the other hand, I still want to do this rounding to the tenths, that's fine. I've gone to the hundredths place, so I can decide to round this to 80 and 3/10. Let's do one more. Here I have 13 and 21 hundredths divided by 11. Now, if I'm not good with my 11's multiplication facts, I could make a list down the side. Hopefully you feel pretty good about the 11's because they're really just the same thing over and over again. But you could always list them if you were having trouble. I know two-digit division gets some people. So 11 doesn't go into 1. 11 does go into 13 once, and I'll do long form here. just to kind of show a different way of doing things. I'll bring my 2 down. I'll bring my decimal up. 11 goes into 22 exactly 2 times. That's 22, so there's nothing left over, and I'll bring down my 1. It doesn't go into 1 at all, so that's 0. So I have my 1 left over. And at this point, I have to add a 0 because I have a remainder, I've got leftovers. I'm not going to deal with a remainder, I'm dealing with decimals, so I want to add a 0 so I can keep going. Because I need to round, if I'm going to round to the thousandths, I need to go to the 10,000ths. So I'm going to have to go 2 more places if I want to get all the way to the 10,000ths and round to the thousandths place. So I'll bring down my 0. Still doesn't go in. 11 doesn't go into 10. Bring down my next 0, and now I've got 100. 11 goes into 199, or 9 times, which is 99. And there's still going to be leftovers here, but I actually don't have to care about them at this point because I've gotten to this 10,000ths place that I was looking for. I can round to the thousandths place now. So my answer for this problem when it's rounded is going to be 1 and 201 thousandths. One thing that I'll point out before we call it quits here is that there's 2 types of scenarios. One is where you already have a decimal. So for example, in this problem, we already had a decimal. We just brought it straight up. The other type is where we're dividing a whole number and we have to add a decimal. It's really no big deal which one it is. You just have to remember for whole numbers, the decimal lives to the right of the whole value. So, to summarize, when you're dealing with a non-terminating decimal, the first thing you're going to remember is that you can keep adding zeros. And you're going to keep adding those zeros as long as it takes until the decimal either terminates or alternatively, you get to a place you want to round to. We always want to know what place we're going to round to because that tells us how long to keep adding zeros. Again, we're going to just keep adding those zeros until we reach that rounded place and go 1 past it. We need that extra decimal value to know whether to round up or to leave it alone. So here are 3 practice problems for you. For each of these, you need to show all your work, first of all, and you need to round each of these to the nearest hundredth. So keep dividing, adding zeros until you reach not the hundredths place, but the thousandths so that you can round. All right, good luck.